The initial quote today comes from Professor Ciavola and Professor Coco. The understanding of some of the specific aspects of coastal storms, from inundation to the morphological changes along the coastline, is becoming increasingly relevant because of the ongoing climatic changes and the ever increasing population pressure along coastlines. Coastal erosion and coastal inundation are the main impacts of coastal storms, and these impacts lead to other consequences for human settlements. Coastal erosion is different from coastal inundation because the former involves significant movement of materials. Sallenger in 2000 produced a useful storm impact scale that categorized impacts to natural barriers resulting from tropical cyclones and extratropical cyclones coastal storms. This scale includes the coupling between forcing processes and the geometry of the coast. There are four variables: R high, that is the highest elevation of swash, induced obviously by waves; the R low, that is the lowest elevation of swash; D high, that is the highest elevation of the first line of the defense, it may be the dune or the berm; and D low, that is the lowest elevation of the dune or berm. Using information about the coastal storm and knowing the location, that measuring the location of these four variables, Sallenger proposed storm impact scale that has four regimes or four stages that we are going to see right now. The first of them is the swash regime, that is the condition where swash is confined to the foreshore of the beach seaward of the dune or berm crest. In this stage, the run-up is confined to the foreshore of the beach. During storms, the foreshore typically erodes and sand is transported offshore. Following the storm, sand is transported onshore gradually over weeks or months. Hence, the eroded sand is replaced and there is little net change to the beach. The second one is collision regime, which occurs when the swash will eventually collide with the base of the dune, forcing dune erosion. The run-up collides with the base of the fore-dune ridge. The collision forces sand to be eroded from the dune and transported offshore and or longshore. Eroded dune sand is not readily returned to the dune, hence there is net erosion. third one is the overwash. In the overwash regime, as runup overtops the dune or berm crest, water can flow landward. Runup exceeds the elevation of the first line of defense, either dune ridge or the berm crest. Sand is transported landward, tens to hundreds of meters, contributing to the net migration of the barrier beach landward. There is net erosion of the beach foreshore and net deposition landward of the dunes. In this imaging, we cannot see waves overtopping the dune crest, but we can see some deposition behind the dune front, the dune crest that was caused by swash. This deposit is we have already seen and is called overwash fan, and this is a meaningful evidence of the overwash process. The last one is the inundation regime that occur when the storm-induced sea level rise is sufficient to completely submerge the barrier and the flows of the barrier are no longer simple overwash. The elevation of the base of swash motion, R low, exceeds the elevation of the first line of defense, D high. Hence, the entire beach or Fordun Ridge system is continuously subaqueous. The limited observation suggests that massive net onshore transport occurs with landward migration of sand bodies on the order of 1 kilometer. This photo is from the World Meteorological Organization and shows a coastal area completely inundated. Let's see one animation in the next frame. Here is a 3D animation of Sallenger storm impact regimes. The swash regime is in the case where the maximum total water level does not exceed the dune toe. The collision regime is in the case that the maximum total water level exceeds the dune toe, eroding the front of the dune. The overwash regime is the case where the maximum total water level exceeds the dune crest, resulting in water overtopping the dune. And the inundation regime is the case where the minimum total water level exceeds the dune crest, typically removing the dune system. One of the key questions of the studies of coastal storms is to determine whether or not there is a cumulative impact of coastal storm grouping. In other words, if the combined erosion of a series of storms is larger than the sum of the average erosion of each one. This graph shows a time series of significant wave height in the black line and peak wave period, the blue line, during the winter of 2013 and 2014, measured offshore of Truquevert, southwestern France. This graph and the table provide an overview of coastal storm serial clustering classification sensitivity due to differences in definition. Data clearly indicate that both the storm definition used and the interval applied may strongly modify the number and duration of storm clusters and the number of storms within a cluster. Assessing storm clustering impacts on coasts implies that we can study each storm event's impact within the cluster and not just consider the cluster as a single large event. The definition of a cluster is imprecise. However, in most cases, the cluster designates a rapid succession of energetic events that make the usual approaches used to assessing single storms inappropriate. Within this figure, Vouduskas and his collaborators in 2012 proposed a conceptual model describing beach morphological evolution phases of steep sloping beaches during consecutive storm events. Their model shows that if no bar or a degenerated bar is present in the surf zone, then the subaerial profile undergoes rapid erosion and the beach profile evolves to a more dissipative state, including nearshore bar growth. Then, morphological change is restricted to the lower or the submerged profile, where most wave attenuation takes place, and the subaerial profile response slows down. They concluded that the antecedent morphological state might initially be the dominant controlling factor of beach response under a series of storm events. So, looking into the figure in phase 1, the beach phase shows rapid erosion or recovery. In phase 2, the morphological change at the eroded subaerial beach decelerates and adaptation of the surf zone bathymetry becomes more important. In phase 3, the beach reaches equilibrium, becomes more resilient to wave forcing, and is vulnerable mostly to increased mean water levels. During coastal storm events, beaches and dunes are eroded and sand is transported offshore. Net cross-shore transport is complex and determined by the balance of transport components due to a range of hydrodynamic processes that may interact non-linearly and are affected by the antecedent beach and shore face topography. Let's see some examples of storm waves and their impacts on the shore. In this example, we are going to see some stages of cliff erosion model developed by Drake and Phipps in 2006. The stage 1 is an early stage with few blocks at cliff base. The stage 2 shows the undercutting of cliff and blocky collapse. In stage 3, overhanging large blocks fail through cliff base unloading. In the stage 4, further undercutting and development of significant cliff overhang. In stage 5, there is a cliff collapse and the development of talus ramp at the cliff base. In this example, we are going to see some impacts of a severe storm in southeastern Brazil. Cape Búzios is a balneary touristic county located 180 kilometers east of Rio de Janeiro City, Brazil. The geological site is composed by metasedimentary and metavolcanic rocks originated from a Cambrian and Ordovician collisional event named Búzios orogeny. The main characteristic of Cape Búzios is distinct structurally controlled beaches. Those are oriented to many directions, as we can see in this map. Those graphs represent wave and wind conditions for Cape Búzios. On the left side, there is the wave graph, and south waves represent swell conditions. Storms occur between southeastern and southwestern directions, and waves can be up to 5 or 6 meters tall. And the right graph represents wind conditions, and northeastern winds represents fair weather conditions and promote fair sea waves. In this research, we have used several methods and materials to determine information about the morphology, the mean grain size distribution, and the beach morphodynamics aspects. For the morphology, we have made systematic surveys of beach profiles with using standard topographic methods to analyze volumetric changes over beach profiles. So we have tested the equilibrium beach profiles and planform stability of pocket beaches and bay beaches. For the mean grain size distribution, we have collected over 265 samples of surface sediment representing beach, shore face, and intercontinental shelf. We have made some statistical parameterization and used a model of transport vectors on the bays and bay beaches. And for determine beach morphodynamics, we have parameterized with embayment scaling parameter, surf scaling parameter, delta and omega parameter, and etc. We have also made some wave simulation for shallow waters using the GHE Mike 21 spectral waves model. Some of the main results of this research can be seen in these two maps. On the left, the map represents the distribution of the mean grain size of underwater sedimentation, and the vectors represent the trends of sediment transport. In North Búzios, this large yellow blur represents silts that indicate the fluvial contribution. The coarser materials are represented by darker colors and indicate relict sands. The map on the right shows a color scale representing declivities and the structural controls that affect mostly central Búzios beaches. This is relevant and can be useful to the understanding of wave energy and sediment distribution. Those are some results of modeling waves on shallow waters using the storm event time series. The maps represent north, south, and central Búzios beaches, and the graph represents the storm event with wave heights in blue and wind velocity in red. The storm event that occurred in April 2010 was unusual. Waves approached the coast from a southeastern direction, which is quite rare. They reached heights above 4 meters, with peak periods of 13 seconds. Note that the waves respond later to the intensity of winds, and we observed a good correlation in terms of their direction. The south sector of Cape Búzios was most exposed to storm waves. Waves higher than 3 meters affected more the north part of embayed beaches. It is interesting to note that this part is also less exposed to fair weather conditions. On the other hand, the northern sector of Búzios is protected from the storm waves. In this case, Cape's projection plays an important role in diminishing the energy of storm waves in this part, creating a low energy environment in a storm event. In the storm event's apex, northern Búzios beaches received waves with HS of 30 centimeters, as storm waves attacked the southern Búzios beaches with HS between 3.5 and 4.5 meters. The central Búzios sector, represented by a commonly protected pocket Ferradura beach, received waves with heights around 3 meters, and significant erosion was detected. Here we can see some selected beach profile stations and their pre, under, and post-storm morphologies. Note that 2 of them have lost more than 2/3 of their sand volumes and did not recover completely for up to 18 months. And finally, here we have some other profiles of nearby beaches. The red line represents the morphology during the storm. Yellow lines represent the morphology of earlier surveys. Some beaches were significantly eroded and some of them not so much. It pretty much depends on beach orientation and the origin of storm waves attack. Coral reefs are highly valued ecosystems as a consequence of their high biological diversity, and the ecosystem services they provide. At the macrogeographic scale, approximately 70% of tropical coral reefs can be found within the major zones of cyclogenesis, corresponding to 7 to 25 degrees north and south of the equator. However, in the equatorial region, reefs are rarely, if ever, exposed to extreme storm events. This is the world map showing coral reefs of the world, superimposed on historical tropical storm tracks between 1842 and 2014. Please note that bright hedge large points correspond to coral reef locations. This is a conceptual model showing ecomorphodynamic approach for coral reefs. Shaded components represent storm effects. Ecomorphodynamics provides a useful framework to examine how storm events can perturb the reef system, leading to fundamental shifts in ecological and geomorphic states. In particular, the framework highlights several aspects of reef dynamics that are critical to understanding storms' influence. First, storms are a set of boundary controls that can force changes in reef health, carbonate cycling, and consequently geomorphic state. Secondly, the influence of storms on short-term carbonate cycling and geomorphic change can be evaluated at the event scale. Thirdly, the system contains feedback that, in case of storms, are temporally specific. Short-term change in incident energy alter ecological communities structure, reef morphology, sedimentation processes, and short-term geomorphic shift in beach and island shorelines. Finally, feedbacks may be nonlinear and can be associated with significant time lags. For instance, short-term stresses, such as storms, may cause changes in the reef that may propagate through the system, altering the carbonate budget and, ultimately, the reef's ecology in the decades to come. A robust understanding of the effects of storm on coral reefs must recognize geographic variations in the frequency and magnitude of storms, that storms affect reef structure and functioning at a range of spatial and temporal scales, and that the net effect of storms is also spatially and temporally variable. It's important to note that coral reef structure is a consequence of a suite of environmental factors, including frequency and intensity of storm events. Intense storms can elevate incident wave heights impacting reefs by an order of magnitude, increasing the energy impacting the forehead and the reef edge by two orders of magnitude. Storm surge also superelevates the water levels across reefs, which fundamentally transforms the reef flat wave environment, allowing much greater swell energy to propagate across reefs and across island surfaces. This image from NOAA illustrates some of the reef zones. Firstly, the forehead that is slopes seaward at steep gradient and is composed of reef-building organisms and reef debris. Then, the reef crest is a narrow-crested or flat-topped zone where calcareous reef framework builders are active, often forming an algal ring, but with little coral development. The reef flats are the most recent expression of coral reef growth at sea level, and the back reef environment that consists of coral communities and reef debris swept landward behind the reef, including sand acorns to mud deposits in lagoonal environments. It's characterized by mostly low energy conditions as waves dissipate their energy over the forehead and reef and is therefore a depositional environment. Let's see some impacts on these reef zones. These tables summarize some of the destructive and constructive effects of coastal storms in the reef zone. In the forereef, the destructive consequences are loss of coral and disappearance of spurs and grooves, and the constructive consequences are sediment production. In the reef flat, the destructive consequences are loss of coral and peel away parts of the reef, and the constructive forces are coral rubble generation and some rubble sedimentary features like rubble ridges or ramparts, rubble tones or spits, exceptionally large boulders. In the back reef, there are no clear effects, either constructive or destructive. And on the reef islands, the destructive consequences are island erosion, shoreline displacement, island disappearance, damage to vegetation and human infrastructure. And the constructive consequence of storms are formation and lateral growth of rubble islands through rubble transport from the reef flats and vertical accretion of sandy and rubble islands through overwash processes. So now let's practice. A 10-year storm wave climate hindcast data is provided. Use a spreadsheet to open it and to do some basic statistical calculations to find out the maximum, the average, the minimum, and the standard deviation for each variable provided. Create a table and a graph with the monthly distribution of storm events. Use those basic statistics, table and graph to write a simple report about the storm wave climate data. This simple report must be sent to my email address. And that is enough for today. See you soon. Take care and be safe.